Perfect. Thank you. So today I'm going to be presenting on some recent work on basically topographic downscaling of climate change projections over the Lake Champlain Basin. And this is work that I've been doing in collaboration with Brian Beckage and Gabriella Bucini, both at the University of Vermont. So just to give you some context, to put this work within a broader framework, this is part of the Vermont EPSCOR project, and we're really interested in doing a full assessment of the local response of precipitation and temperature to climate change over the Lake Champlain Basin. And relevant to this presentation, we want to know whether we can take global climate model projections and usefully downscale them to 1 kilometer for hydrologic and land use modeling. And this really involves 2 questions, right? So 1, can we add value down to 1 kilometer? And 2, can those hydrologic and land use models actually use that added value? And then finally, we love to put error bars on everything. So we want to know critical uncertainties, basically in predicting climate change impacts over this region. And this is simply a picture of the Lake Champlain Basin that I took from Burlington. So to get down to 1 kilometer, what we're going to do is we're going to leverage topographic data to create these very high resolution climate scenarios. So we're going to start with an intermediately downscaled products, and there are a variety of these around, BCSD, BCCA, among others. So they're about at 1/8 of a degree or 12 kilometers, and we want to go down to 30 arc seconds or 1 kilometer using elevation data. So I have our domain on the right here. And it's most of northern Vermont and then southern Quebec. And overlaying on that is the 1/8 of a degree grid and topography. So we really just use 4 simple steps. We're going to derive observed temperature and precipitation elevation adjustments from station data. We're going to translate our variables to a reference elevation using these adjustments. And then we're going to interpolate to increase the spatial resolution. And then finally, we're going to pull everything together to get to our high resolution temperature and precipitation data set by modifying that interpolated data using a high resolution DEM. So the first step in this is to derive these elevation adjustments. And so to do this, we just assumed a functional form and use maximum likelihood estimation. So on the left side, I have the 4 watersheds of Lake Champlain, our domain outlined in red, and then black dots represent all of the stations that we use to derive these elevation adjustments. Our assumed functional forms are on the right. So for temperature, we're a functional form of both elevation and latitude. And then for precipitation, just of elevation. So we actually checked within our domain to make sure that there was no statistically significant relationship between precipitation and latitude. And so simply, this is multiple linear regression that comes out of multiple sources. The assumed functional form for precipitation is from the literature. It's from Liston and Elder, who in 2006 used this equation for a high-resolution weather generator. And all we do is simply use maximum likelihood estimation to derive gamma and chi, which are our 2 variables of interest that are going to allow us to do these elevation adjustments. So this is what the temperature elevation adjustment derivation looks like. So remember I said we're both a function of latitude and of elevation, so we did a multiple linear regression. So you have the average latitude, and then you have the boundary latitude, so this would be the southern latitude, this would be the northern latitude, and then these are annually averaged temperature, and these are basically the elevations of all the stations in our domain. And what we end up with is the elevation adjustment, and for temperature this is simply a lapse rate. And so here we have negative 5.05 times 10 to the negative third, and that would be in degrees Celsius per meter. So now that we have our elevation adjustments, we're going to refine our climate data based on these elevation adjustments that we just derived, and then also interpolation. So we take, for example, an 1/8 of a degree precipitation field. So we have it at its coarse resolution, and we're going to use chi and the change in elevation from the 1/8 of a degree DEM to pull it down to a reference elevation, which is a rounded average of our domain elevation. So we're pulling it here to 250 meters. And then we're going to do our interpolation, and you can choose your favorite flavor of interpolation. We use inverse distance weighted, but you could use bilinear kriging, depending on your preferences for how smooth you want your ultimate product to be. And once we've interpolated, we can go to the high resolution DEM, we can use the same elevation adjustments, and we can pull the data back to their actual elevation, or the actual elevation is defined by a 30 arcsecond DEM. So this is what ends up falling out when you do this downscaling. So what you have is this is an eighth of a degree product on the left, so this is our initial product, and now we're down to 30 arcseconds on the right, and we have precipitation on top, temperature on bottom. This is for just a random day that I pulled. This is just an example of the output. I haven't mentioned yet, but we're doing this for multiple GCMs for the CMIP5 archive. So this is BCC CSM. And the intermediate downscaled product that we're starting with is bias corrected with constructed analogs, or BCCA. And so basically, you know, the native resolution of a GCM is not 12 kilometers. We need BCCA to both get us down to 12 kilometers and also bias correct before we do this extra downscaling. And as I mentioned, we use inverse distance weighting. In here, I didn't write it on the slide, but we used a weighting power of 2, and we used 9 nearest neighbors. But again, you can choose whatever your favorite interpolation scheme and parameters are to get the fields that you want. So I've showed you that we have more resolution, but of course that's not the question. The question is, do we add any value? So this is an example of output. So I just chose one station, and this is Mount Mansfield. And this should give us our most dramatic example, because Mount Mansfield is the highest station in our domain, about 1,200 meters. And what I have here in the panels is the station observations in the upper left. These are the Maurer observations. So this is an eighth of a degree gridded observational data set. I have the BCCA data. So this is the intermediately downscaled data. This is at an eighth of a degree. Interpolation and adjustment. So this is our product. And then I take the differences between BCCA just interpolated here and our interpolation and adjustment difference. So that's our product minus the station observations. And then the red line just indicates the mean value for each of these panels. And these are daily distributions of temperature. We're interested in daily distributions of temperature. So a few things to note here. So this is basically you can think of the differences between these two. This is what happens when you go to a gridded observational data set. This is some interpolation here, which is kind of degrading the signal. BCCA, so this is targeted to Maurer observations. So these means are going to be practically the same, but the daily distribution of temperature is going to be a function of the GCM, not of the Maurer observations. So if we go down to our results, what we're looking at is an interpolation difference, and the difference between interpolation and adjustment, and that and the station observations. So here what we're hoping for is shorter bars, and that's exactly what we get. And this is somewhat expected, right? Because there's a clear relationship between temperature and elevation, and we're doing we're basically doing a better job of capturing what elevation this data is at. And so we see that the station data, 1.3 degrees Celsius, these are the annual averages. The interpolation alone is 5.4. The interpolation and adjustment is 2.8. So great, we're adding value. This is a good thing. But what we're actually interested in is precipitation, because temperature is not as important when we're talking about hydrologic applications, which is what we're particularly interested in. So now we're going to look at precipitation. And I have the same panel, so I won't go through them all. The blue line, again, is the average. We did take off the 0 to 1 millimeter per day bar so that the y-axis stays reasonable. But when you look at the averages, that includes all precipitation. But the histograms take off the 0 to 1 millimeter per day. So you can see the results are not nearly as dramatic. And with most GCMs, we overestimate the low precipitation events, and we underestimate the high precipitation events. But if you do look closely, basically at the differences, there is some improvement, basically in the daily distributions of precipitation after you do the interpolation and adjustment. And then if you just look at the averages, you see this. So the station is 5.4 millimeters per day. Interpolation alone, we're at 3.3. And then if we go interpolation and adjustment, we get a little bit more precipitation. So that's helping out. So next steps, that was just for one station. What we're doing at the moment is we're basically binning our stations into high and low elevation and making composite distributions. So basically distributions that capture the multiple stations worth of daily temperature and precipitation data, and we're looking for that added value of elevation adjustments versus interpolation alone. And we also want to compare these magnitudes of the elevation adjustments to variability among the GCMs. So basically, this takes time, this takes computational power. Is it worth it, or should we spend our time picking the GCM that does the best job of simulating the daily distributions of temperature and precipitation? Is that where we should prioritize? And then assess the sensitivity to the spatial interpolation method. So I mentioned you could basically choose your interpolation method. So is it at all sensitive to that choice? We also acknowledge that, and this is kind of further down the road, that the climate change scenarios, even after this adjustment, won't do a great job with precipitation extremes. This in no way basically does any compensation for that. So we're actively developing methods that will basically layer on distributions of extreme events. And then finally, applying these scenarios to downstream EPSCOR applications, including hydrologic and agent-based modeling, which is the land use land cover modeling. And here I just have an example of the Mad River watershed where we have RESIS deployed and is using some of these climate scenarios. Thank you.
Thanks. We have time for a question or two. Actually,
people are hungry.
Yeah.
So if you go back a couple slides.
Sure. I think I use this. Which one?
Or this one on the precipitation. So
Okay.
you had a cutoff at 0.1 millimeter per day.
Yes.
And I was just wondering if you applied, you did analog on each of them, or that changed the sampling. So for example, if on the Mauer data set you had some 0.1 millimeter and you cut it off from that sampling, did you remove the same date from the other data set, or that was different?
No, different. So just it was just taking the 0 through 1 millimeter a day, because these are just statistical averages over a 30-year period. So it was just taking the 0 through 1 millimeter per day bar and removing it. And to be fair, those 0 through 1 millimeter per day bars are going to be different sizes across those different data sets.
Yeah, so do you think this is changing some of your, this is changing the sampling, and so do you think this is changing some of your statistical conclusion? Or is
So I mean, if we move forward, if I actually took that off and well, I think so. If we did a formal, if I presented a formal statistical analysis of whether this was adding value, that 0 through 1 millimeter per day bar would have to be back on. But just for presentation purposes is why I took it off, because otherwise, you know, it's a much larger bar than the rest of them.
I have a question. Do you plan to serve the data online, or the method for the data online? I imagine it's big.
Yeah, the data ends up being big, even for such a small region. So right now it's served internally on the Vermont EPSCOR servers. If people are interested in the data, they can feel free to contact me. I don't know if there's any plans to make it more broadly available. But the method is we're writing it up, and hopefully we'll have that paper submitted in January. So it'll be open source in that sense, and people could also email us for the code.
Okay.
Happy to share.
Thanks, and thank everybody for coming. We'll have 2 more sessions tomorrow. There'll be a poster session in the morning and 2 talk sessions in the afternoon, and hope to see some of you there. Thanks. And thanks to all our speakers for great talks.